from Edward and Veracio. Thank you for joining us today. My name is Kumo, and I'm a course advisor for ECT. And today, today's webinar will be presented by Professor Kalam, who is the EIT professor. And I would just like to turn your attention to the notifications and the sounds. And I would like you to just turn them off while the presentation is going on. This is just to minimize any sort of interruptions that may occur while we are going on with the presentation. And we also have a Q&A function where you can put your questions in the chat, in the Q&A function box, and then Professor Kalam will have an opportunity closer to the end of the presentation to answer any questions you may have. So if it's questions about the webinar itself, Dr. Kalam will take care of that. And then if it's about the courses and so forth that we're offering, I'll be taking care of that. But we'll take the questions at the end of the presentation. And with regards to the certificate of attendance, it will be sent to you, as well as the copy of slides and the video recordings. With the video recordings and the slides, the copy will be sent to you within the next 2 business days. So that will be sent via email along with the certificate of attendance, but that will be sent within 4 business days. So if you don't find the copy of the slides and the recording or the certificate of attendance in your inbox, please kindly check your spam or junk mail. Sometimes they do land there. And with the form and the QR code that will be presented later on for the certificate of attendance, you'll need to fill out a form, and that form will ensure that you receive the copy of the slides and the certificate of attendance. So if you don't do it within 2 days after the presentation, the link expires. So I would suggest that you do the fill in the form within 2 business days. The sooner the better, really. And just to let you guys know a little bit about ECT, for those of you who don't know about ECT, ECT is an engineering specialist which is affiliated to the well-established EIT in Australia, the Engineering Institute of Technology. So with ECT, similarly to EIT, we do offer industry-driven programs, which is all made possible by our professors who are industry experts, as well as the fact that we have UK recognized education, and we've got lecturers and instructors that are in the industry. So they are professionals and specialists in the industry. And what really sets us apart is our unique delivery model that we offer to our students around the world. And with regards to the event conduct, please, there is no recording allowed of this webinar because it will be sent to you. And if you can just follow my instructions to have a smooth sailing webinar today. And as I've mentioned, today's topic will be presented by Professor Kalam. And the topic for today is about the mysteries, the vanishing vault. Why did the circuit breaker trip with no recorded fault? Professor Kalam, you may take control and take it away. Thank you.
Thank you very much, Kumo, for that kind introduction. And thank you very much, Edward and Veracio, for coming in today's presentation. So the presentation that I want to give is on mysteries. There are a lot of mysteries in engineering, and in particular in electrical engineering, which is my background. And you find that there are no correct answers, and it's very hard, especially those people who come from the normal route of universities and then coming to workforce, in the first 5 years, they do not know why these mysteries happen. And some of them, very senior engineers, don't know the answer to these mysteries, but these do happen. And that's what we are going to talk about. So, in order to make the presentation more presentable, I will be minimizing the use of mathematics. I'll be minimizing the use of boring lectures. This particular presentation that you are going to go through is going to be a great mixture of forensic analysis, protection coordination, and non-linear system behavior. So, welcome to all of you. And I see another one has joined in. So, welcome to all of you uh, in today's presentation. And remember, we are not looking for any textbook type of faults. In fact, you will not get this from the textbook at all. You'll not be able to find this type of example from textbook. It's not in textbook, but it happens. So what we are going to look is at the anomalies that keeps asset managers awake at night. Situation where the data doesn't immediately match the outcome. And, and that's what we are going to look at, my friends. And these are the type of presentation that I'll be going to go through every month on this last Thursday of the month for the ECT. Now, as I told you, the the presentation is on the vanishing fault, and the circuit breaker did not trip. You know that when there's a fault, the protection sees the fault, and it gives orders to a mechanical device which is called circuit breaker for it to operate, and that's basically a switch. And the switch turns on and off. When it is on, the system is working. When it's off, it is off the circuit. That's it. Very simple. But this one, there was no fault, and the circuit breaker tripped. That means there was no power. If there's no power, my friends, remember, there's no dollars, there's no pounds, there's none of these things are there. So this definitely did happen, and I'm trying to go through the analysis. But before doing all that, let me explain to you who I am, because many of you may not know me. I work at both Victoria University and EIT. I'm also working as an academic director in a private college, which is Texila College in Australia. I've got my own consulting company. I'm editor-in-chief of Australian Journal of Electrical and Electronic Engineering. I've got a lot of appointments throughout the world, and I've published around 600 publications now, and about 60 PhDs and DN students have graduated under my supervision. I'm a public university and motivational lecturer, and I'm consultant for a number of electricity supply industries in Australia and overseas. And I also, as a sideline, help the universities in change management plan, especially the universities which are dealing with engineering education. My own education, you'll be surprised, I graduated from Bath, from England, myself, about 200 years back, but I did graduate from England. And then I did my PhD from there. I did my master's from in US in Oklahoma, and I did my initial bachelor's of engineering degree and bachelor of science degrees, a double degree program from two universities in India. I'm a member of majority of the professional bodies, in particular those which has got affiliations with electrical engineering. So much for myself. The agenda today is written, and I'll be talking about the mystery itself, the objectives of our learning, give you an overview, talk to you about assumptions, and go through the investigations and resolution of the case and what lesson we learn. Okay, the first thing that comes in mind is why study these mysteries, especially the mysteries in electrical engineering? And the answer to that question is very simple, my friend. The answer to this question is very simple. Because if you are going for a post-graduation engineering position, you have to get out of that trend that you've got in your undergraduate qualification when you were formula-based thinking to a completely different thing, which is judgment-based. So no more formula-based, judgment-based. And mysteries will sharpen your diagnostic skills and professional intuition. In this presentation, I will try to act of my favorite character. And you might have seen this favorite character of mine who was in the play called Pink Panther. I don't know whether you've seen that, the television series Pink Panther, where Peter Sellers was Inspector Jack Clouseau. So I'll be like that. Or some of you who haven't seen Pink Panther, if you have seen Columbo, there Peter Falk was the Lieutenant Columbo. And exactly like that, I'll try and mimic them. If at all you haven't seen those two uh, television series, then maybe you've read a book of Sherlock Holmes and, think about from that angle. So these are the things that that is what I'm going to mimic. That's what I'm going to talk about. That is the style I'm going to take. So, my friend, textbook has got no correlation with the real system. Not at all. It's all good in formula and all those. No correlation at all, my friend. Textbook has got nothing over there. So, many times you will find that the data that you have is incomplete or misleading. And you, as an engineer, must decide before all facts are known. So you may solve the problem in 1 year time, but your decision has to be as quickly as possible. Here, in engineering in particular, safety is very important, reliability is very important, and if it don't do that, it's going to be very expensive. And it's very expensive, your electricity prices will be high. So therefore, we need to study these mysteries. So now, let me look at the engineer, which is a detective. I told you right in the beginning that there is a gap between theory and actual reality. And there are importance of event recorders and SER, which is the sequence event recorder, or the waveform capture, which is ComTrade. These are some of the power systems, events, and ensuring system reliability tools. So both of these, they exchange the transient data between systems and are essential for compliance with industry standards. And my friend, If you were going to do these as a postgraduate study, you would be focusing on steady state or known transient model. In the field itself, the missing data is more important than the recorded data. The missing data is more important. So here in the mystery, my framework has got 4 points: observation, hypothesis, simulation, and verification. And now let us see the objectives of this learning exercise that we are going to do. And my friend, I want to make it very clear to you right in the beginning. My aim is not to memorize causes, but to develop a methodical investigative mindset. I want to ingrain in you, in your mind, how to investigate methodically. So my objective is basically to make you understand what is the unexplained breaker trips. I want you to look at the relay logic or any blind spots. I want you to investigate the DC and auxiliary systems and apply professional diagnostic method. I'm not believer of layman type of methods. Professional diagnostic methods. So the idea is not for you to memorize. The idea is not for you to memorize, my friend. So the objective is very clear. The structure of the mystery case, why the transient faults matter, and what actually happened. So let's go back to my detective series, Inspector Colombo and Inspector Jack Clouseau. Sorry, Lieutenant Colombo and Inspector Clouseau. How will they tackle the problem? If they were an engineer, they would have done that. There is a industry. Okay. An industry is there and a feeder tripped. And this was unexpected because there was no fault. There was no lightning strike. There was no shunt fault. There was no series fault. But still, the feeder tripped. There was no protection problem. The relay did not record any anomaly. The SCADA, which is supervisory control and data acquisition, it was normal before and after. And my friend, the system restored without an issue. So I can't understand what really happened. So I go deeply into the matter and set the scene. This is a rural feeder. I know that there is a circuit breaker, and I understand there's a type and rating of the circuit breaker. And remember, there's an environmental conditions. Environment plays a very important part. And in England, where you see 4 seasons in one day, right, you can find this a very big problem. So the question is that, why is this a mystery, my friend? Why is this a mystery? Okay. The first thing is that the breaker has tripped. That itself is a mystery. It is random. You can't expect the breaker. There was no fault. The protection did not get the indication that there is a fault. The protection did not see it. So it did not send any signal to the circuit breaker. Why the hell did the circuit breaker operate? And the other thing is that operators could not replicate the system, the issue. Remember, my friend, in real protection system, is quite different than what you learn from textbooks. So my question to you, if nothing is wrong, why did the breaker open? Now, normally I would have asked you, but to answer these questions and work with me, but because of the time, it's only 1 hour. Therefore, I'll give my own answers and let you ponder over the question itself. Because I want you to be curious. I want you to see your skepticism. Okay, why did the breaker operate? Because in fact, breaker do not trip randomly. Breaker will only trip when the signal comes from the protection. As I told you, there was no recorded overcurrent on earth fault. There was no visible equipment damage, yet the trip was real and it disrupted the system. So I go back to my theoretical thing that I have done in my undergraduate studies and see what I can assume initially when this thing happens. The first thing that comes, maybe the relay malfunction. Maybe the relay goofed up. That was first. If the relay goofed up, it sent a signal to the breaker to operate, but it didn't send any signal. So the breaker did operate by its own self. My second assumption is that the SCADA failure was there. And therefore, I got incorrect information was given to CTs and VTs, and therefore the relay sent a signal for the circuit breaker to operate. That did not happen either. And the third, which is a great possibility, there was an error from the part of the operator. Human errors are the worst thing that you can happen. If you look at Segre, they say 60% of the fault is due to human errors. All these three assumptions that I have made, whether it's of the relay, whether it's of the SCADA, whether it's the operator, all of them are incorrect. Okay? So the answer to your question is that all your assumptions that you had were all incorrect. So do not jump to conclusions, my friend, because you will never know the true cause if you jump to the conclusion. And for God's sake, take responsibility, because you have that urgent desire to blame the instrument immediately. You say, oh, protection was the problem. SCADA was a problem. Operator was a problem, right? Don't do that mistake. So don't come to the conclusion too early. Try and find out what really happened. Okay. A bit on what does relay do? Because relay is very much like a human being. And if I can give you an analogy of relay and a human being, and if I can give my own example, my brains is the relay. If someone comes and does damage to me, hits me, thrashes me, cause trouble to me, my brain doesn't do anything except give signal to my hands and legs to move. Exactly in the same manner, the protection only sees and does all the calculations and understands that something has gone wrong, sends a signal to the circuit breaker to operate, just like my hand and legs are moving. The protection relay is rated at 110 volts and 5 amps or 1 amp. In the actual industry, I mean, I was talking about 11 kV system. You talk about 200 kV system, you talk about 400 kV system, whatever system you want to come. You have to bring it down to 110 volts or 1 amp or 5 amps, because that is how the rating is. So you have to step it down. So how do you step it down? You use current transformer and voltage transformer. So if there is current, there is voltage, bring it down to the level of the protection system that you have. And then there are some logics over there, if you want to have an impedance, voltage over current, okay. If you want to talk about overcurrent, you have a threshold of, say, 5 amps, and over that is over current, exactly in the same manner, over voltage, all these type of differential relays and directional relays and distance relays, you name it. And many times, as I told you, when I talked about overcurrent, if the current goes more than 5 amps, 15 amps, whatever you decide as your threshold, that is your basis for your decision. So relay only sees a representation of reality, not the reality itself, my friends. So you see this diagram that I've got. Here's the power system. Here's all the CTs and the VTs. And this is the relay. Relay sends the signal for the circuit breaker to operate. The work is being done by this guy, circuit breaker. So, my friend, let us see the vanishing fault. And this is my taxonomy that is going to guide my investigation. First thing is the transient faults. Transient faults are intermittent in nature. It happens a very small period of time and cause substantial damage to the system. It could be high impedance fault, which is intermittent. It could be something which is non-electrical, which has triggered the fault, or it could be the power system artifacts. So let us see. Let us see the transient fault. And the best type of example that I can think of transient fault is lightning strike. Lightning strikes for a very short period of time, a very high value of voltage or whatever is induced over there. Or in the olden days, lightning strike was a very big factor. Whenever there was lightning, you would have a huge problem. Now, every building, industrial site, they have got surge arresters and they catch the lightning. So there's no problem. No major damages occur. So everyone takes lightning strike as something very simple. It's not very simple. Nowadays, switching surges has become more difficult. That means the series type of fault, and the insulation might break down. So all these faults are there, may clear themselves before logging systems respond. As far as the transient fault is concerned, my friends, okay, they leave no trace. Because the duration of the fault is a lot lower than the relay event window. I told you, for a very short period of time. Peak current could be clipped by the CT saturation. You've heard about that BH curve. And the event recorder did not do any triggering.
Hold on, Dr. Kalam. I
Yes,
just
please.
want to find out from the attendees if they can see the slides moving. If they
Oh,
could just
sorry.
give me, if
I'm
they could
very
just give
sorry.
me
I
a
thought
thumbs
you've
up.
done that. I'm very sorry.
Yeah, I mean, I see that you have taken control, but I want to know if they can see on their side, because
Yeah.
on my side it's just been it's still on the topic. Okay, yes, they can see the slides. It's fine. Then
Yeah,
it's
yes.
just on my end, so
Edward,
it doesn't matter.
Edward has immediately responded. It's your problem. Even
Yeah.
as a matter of fact, Navagako has also said that he can see and hear me very clearly.
Yeah.
I'm
So I
glad you
think
can't hear. I'm so glad, Kumo, you can't hear, because then you would think that this guy is crazy. He's talking like he's talking like Inspector Clouseau and Lieutenant Colombo. Okay,
Thank
and
you so
Veracio
much.
can see it. Hooray!
Yeah,
Veracio can also see it.
sure, no
Everyone can
problem.
see it.
Go ahead. I'm sorry about that.
Okay, I'm glad you interrupted. Now, I did talk about high impedance fault. My friends, this is a very important event. And this event, which is the high impedance fault, occurs when an energized conductor makes contact with a high resistance non metallic surfaces such as dry soil, pavement, grass, or a tree branch, resulting in a fault current which is so low that it cannot be detected by your standard overcurrent relay. You understand? You can't be. It can't be detected. So the value is so low, the value of the fault current is so low that your overcurrent can't even detect it. So that is a high impedance fault, right? And impact is tremendous. Impact is tremendous. And there's a lot of challenges in this. Detecting high impedance fault is very difficult. And this behavior changes under varying load conditions. My friend, let us see the fault characteristics of an high impedance fault. Okay, because the high impedance fault, because the current is very small, very low, overcurrent protection cannot work. But this fault is so dangerous that it can make your system unstable. So it can make your system unstable, and this can cause issues. My friend, this is definitely going to cause issues for you, because, okay, you will have issues like public safety, fire hazard, equipment damage, and operational challenge. Look at this equipment. Look at this coil, how it is burned. See, the current is very low, intermittent arcing takes place, the arcing behavior is unstable, invisible to protection, connection might be loose, contaminated insulators, carbonized cable termination, and this is what happens, as you can see in this screen. The other thing I told you about is the saturation of CTs. Saturation of CTs. Okay. If the current does not decay after a trip command, the breaker failure logic initiates a backup tripping. So the breaker failure protection, and there's a device number called 50BF. BF is breaker failure. It acts like a critical backup, initiating a trip of surrounding breakers if a primary breaker fail to interrupt fault current within, say, 6 to 12 cycles. That's about 100 to 150 milliseconds, 200 milliseconds. So this is after the trip signal is issued. If this triggers when a trip command is issued, then after a delay, the current persists. So you find that there is an offset. Can you see this offset? So this is your primary current, and look at the offset. Look at the offset. That's a DC offset. So the core has saturated because it has crossed the limit of the secondary current, and relay sees a reduced or distorted signal. So relay doesn't think there's a problem. Relay doesn't think it's a problem. So my friend, at that time, I want to just go over it and tell you what the breaker self-protection function does. In particular, you have heard about SF6 breakers, you heard about vacuum pressure monitoring breakers, all sorts of breakers are there, okay, which has got spring charging in supervision, it has got the internal pressure monitoring, it has got anti-pumping logic, all this is there. Look at the contacts, all that. There's a fixed contact, there's a moving contact, and that's how it works. So many trips are occurred locally by the breaker, not by the relay. It's not the poor relay which is at the fault. The breaker itself has initiated the tripping. Also, if you look at the auxiliary causes or the mechanical, remember I told you the mechanical device. Okay, there could be a wire could be loose, could be the vibration has induced a contact bounce, could be the relay is chattering, the auxiliary relays. And remember, it's a mechanical device. So now you might say, you 14 people that are attending today's presentation might say, that why should I bother? I'm an electrical engineer. My friend, in the field, you're not an electrical engineer. You have to look at all facets. There's a mechanical problem, think mechanically, my friend. If it's a chemical problem, think chemically. So you as an electrical engineer now have to think mechanically. So let me see my clues that I've got. First clue that I have is that the momentary disturbance, and the log has indicated that there has been a disturbance. There's no doubt about it, there has been a disturbance. The disturbance has not been large enough for my protection to work, but there has been a disturbance. The protection did not see it as a permanent fault. And one more thing, when I was looking around it with my magnifying glass all around, right, with all my tools, I am the Inspector Clouseau. I found vegetable over there. Vegetation, close proximity to the line. I found that too. So, my friend, I've got this clue at least. Some clue I've got. So, therefore, my friends, I started the engineering investigation. This is where I started my engineering work. I looked at it and tried to consider the transient fault. Is it the transient fault? Is there an arc over the potential? Is there a wind-induced conductor movement? You've seen all sorts of wind, cyclone, typhoon, all sorts of things. Okay? So here, your engineering judgment. First was the clue. The second was the engineering judgment. Now, after that, I want to look at the coordination of the protection. Definitely, there is a risk of miscoordination. Definitely, there is transience period, there is very short duration. And definitely, the relay sensitivity is there. It's oversensitive. These things are oversensitive to the relay settings. So, my friends, I now look at my protection. It is a typical inverse time overcurrent element. That means I is proportional to the inversely proportional to time. So if the time increases, the current decreases. And this is a device number called 5051 for overcurrent protection. And you find that inverse time overcurrent elements may not operate for short duration. Or as I've shown you, the current was distorted. And this is a very big problem. So sometimes you will have to use something else. So there's a circuit breaker coil, it did not operate. So therefore, I go to my next device, again, that is an earth fault protection. And this one is a 50N, 51N, N is for neutral. This is a time over current protection. And this too does not operate for short duration or distorted currents. Okay. Then I look at a third device. My third device is an earth fault protection. And this one also does not operate for short duration or distorted current. All of the three that I've talked to you about does not operate for short duration or distorted current. Although there are a lot of functions in there, it does not operate. And by the way, it costs you anything between $8,000 to $12,000 to buy any of these equipment. Nothing is cheap, my friend. So let us look at the role of the DC. I told you it started saturation and there was that DC offset. And when there is unintended leakage or wiring fault, this can energize the trip coil without any primary fault. DC trip circuits uses a DC supply, protective relay contacts, and a trip coil, which initiates the breaker opening. Unintended spurious trip occurs due to insulation degradation, due to moisture, due to wiring fault, due to bypass protective circuits and contacts. These issues can be mitigated by monitoring for ground fault and ensuring proper cable insulation. So this is a question of integrity of DC. It's a question of DC fault is causing the trip, and the trip is false. And this is, in most cases, an engineer will overlook this. And for those who are very keen to know what happens, then I've explained to you how the DC trip circuit works, because any unintended leakage can energize the trip coil. There's no primary fault, but still it's energized because of that leakage or the wiring faults. So I've covered that too. Now let me look at the environment. And in particular in England, where it's so cold, it's a dabby weather, I was there for 3 months in December to February. And believe me, it was raining, could not see a blue sky. I did not see blue sky in my PhD time, which was about 2 years that I spent in Bath. So you've got moisture ingress, my friend. And over there, the temperature is extreme because of it's an island, England, and because of the Atlantic Ocean on one side, Europe on the other side. And there is dust and contamination. All these can impact your system. And the anecdote that I'm talking about, these are the non-electrical causes: moisture, extreme temperature, dust and contamination. Look at what is done to that machine. My friend, I told you, majority of the problem happened because of the human being, the operators. I don't know why including myself, I have a bad habit of poking my hands everywhere. And remember, we are talking about system. I've taken everything as system. You are also a part of the system, my friend. You are also a part of the system. So that maintenance induced latent fault, even when I'm doing the maintenance, right? This is you're absolutely right. Human factors are very important. And incorrect settings updates are there, and temporary, the test links are left installed. All that can cause a lot of problems. I mean, I do remember a joke when I was a student. They were talking about a pilotless aeroplane that Russia had discovered, and the first flight was from Moscow to Stalingrad. And what happened was that they had few visitors, 20, 30 people who were visitors. They were there. They saw that the pilot come in. They saw that when they saw the pilot, they were very scared. They said, "What the hell? Why is the pilot? It's a pilotless plane." And then they saw two dogs coming in. They asked, "Why is this two dogs?" They said, "As soon as the pilot touches something, the dog will bite." So exactly, we should have dogs around. As soon as human being touches anything, it'll bite, because you are part of the system also. My friend, the recorders, I've talked about SCR, the CompTrad. If there's no record, no event. Resolution and triggering matters. Logs require interpretation. That's why continuously there's a logging going on in a substation. And remember, as an engineer, you're sitting in the CBD of London or wherever you're sitting over there, right? And at the rural area is your substation. You will ask first thing, give me the log events of what actually happened. So therefore, my friend, we have to do the investigation in a very structured manner. Don't lose any evidence. Preserve everything, because you'll again be using it later on. And you don't want to have the same problem again. Review all your setting and logic. Inspect your primary equipment. Test your DC and auxiliary circuits. So remember, two things are very important: discipline and documentation. All documentation must be kept. And then, when you're doing the investigation, ask the right question. You might sound silly. You might go and say, what changed recently? Ah, do you think the weather was bad? Oh, did anything almost fail? Get other people to answer your question that you have in mind. And remember, any good questions will reveal the hidden causes. So the resolution of the case in this one is simple. There was moisture in the marshalling kiosk. There was a DC trip circuit leakage, and momentarily there was unintended trip. So this environmental issue which had nothing to do with the relays, which had nothing to do with the recorders, which had nothing to do with the breakers, that caused the breaker to trip. That's how there was DC trip leakage, and that sent a signal inside the system itself to trip. And therefore, it was an uninterrupted trip. So can you understand? Just a simple thing like environmental issues have caused this mystery. Okay. As I told you right in the beginning, no fault was recorded. There was no primary fault current. Even if it was there, it was so low that your overcurrent did not catch it. Relay never asserted itself. and the trip initiated in the contract control circuit. So can you understand how my initial mystery started? All these things were exactly the reason right in the beginning that I talked to you about. And what do students miss? Many of you do not understand what the DC system is. Many of you do not understand what the environmental effects are. Many of you do not know what the human machine interfaces are. So you have to broaden your thinking. So, how this appears in practice? Look, my friend, in the actual system, there's going to be nuisance strip. If you're going to have nuisance strip, the confidence of the customers will get out from your hand. If you lose your customer, you lose dollars, you lose lost pounds. And also remember, there's a regulation, regulatory settings are there. The scrutiny is by the regulator general, and they might penalize you further. So there are consequences for such type of action, even if it's unexplained trips. You can't tell the regulator general that I did not expect this. So this is where your engineering judgment, which was under uncertainty, comes into place. Therefore, remember, do the technical analysis, take professional responsibility. Decisions without complete data has got no meaning. Do the risk and cost, balance it together. Because the more the risk, the more expensive it will become. But there is risk in everything that you do. Even crossing the road where you live in from one side to the other side. The other side, 7-Eleven, you have to cross. There is a chance that a truck might come and hit you. That does not mean that you will not cross the road. So how you can mitigate that risk? And knowing when to escalate, that is where your professional responsibility will come. Now, my friend, I would have asked you this question. Would you reclose immediately? What evidence would you demand? When is replacement justified? Think about these type of questions. Because by debating such type of questions, you will get multiple valid viewpoints, and you might be all right. I don't know. So what is the takeaway that we have from this mystery? First takeaway is that not all trips are electrical faults. Remember, protection has blind spots. Remember always, good engineers, you can call an engineer Akhtar Kalam, you can call engineer Lieutenant Colombo, you can call engineer Inspector Clouseau. Remember, good engineers are the one who are good detectives. You can call them Sherlock Holmes also. My friend, you need to deepen the investigation. Look at the load variation through sensitivity. Look at the local weather impact. Look at the soil and environmental conditions. Once you do all that thing, you will be able to find the root cause of the mystery. Was the arc over due to the vegetation? I told you near that 11 kV industrial system, there was vegetation was there. Right in the beginning, I gave you the clue. I also talked about the transient and self-clearing nature. I also talked about the protection activated before clearing. But my friends, some of the factors we missed. We missed some of the factors. There was no transient monitoring devices in place. Assumption was that everything is a permanent fault. You assume that inadequate vegetation clearance was planned. So, as a professional engineer, Your insight would have been to show that there is an importance of SCADA system. High speed fault recorders are routine things which is there, and environmental risk is right in the beginning. You should look around and find out. This is the first thing I would do when I visit a substation. Look around and see. Just a glance. I'm not asking you to take some sort of stethoscope or something like that and try and measure the temperature over there. No, not at all. But make sure that you have some sort of checklist. Review the relay coordination, include your transient scenarios, do the vegetation and environmental inspection. Also remember, my friends, also remember that there are regulatory implications, and some of them, I've forgotten all the British one. In Australia, we have the AS/NZS 3000 for such type of condition, or you can find out from the IEC one. Okay. As a professional engineer, what lesson have you learned from today's presentation? Is as follows. Transient faults can cause breaker trips without any permanent fault. Data analysis is crucial. Coordination saves operational cost. Think beyond fault currents. Respect auxiliary system. Investigate systematically. So, my friend, in conclusion, what I want to say, understanding the transient phenomena prevents misdiagnosis. Proactive engineering will reduce the downtime. If it reduces the downtime, your dollar earning capacity will increase and you will not lose customer. If there is absence of evidence is not evidence of absence. So think about it philosophically. Think about this as an engineering practice. And with that, I have completed my presentation. Humo, our presentation has been completed. I just want to open it for any questions and answers and for any real world insight that you may have. And uh, that's all I had to say. Thank you very much. And I just
Uh,
wanted to remind you that we will be having again next month at Thursday, all that thing Kumo will talk about. And if there are any questions, I'd be more than happy to answer. So, Kumo, if you can start your session.
Okay, sure. Yeah, you guys can. Number
Yeah,
one,
that's what
thank
I'm
you for.
doing. Then,
Okay, thank you for that, Dr. Kalam. That was very insightful. And thanks to your investigative skills, I'm sure the attendees have learned how to investigate these types of problems. And thank you to our attendees for attending. We do appreciate your presence and the time you've taken to actually be with us and attend this. So I will be just telling you about our upcoming courses for ECT, for the Engineering College of Technology. So we've got both our bachelor's industrial automation and electrical engineering starting in 2 months in September. And then thereafter, we'll have another intake in February. Similarly, with our Master of Science in Power System Analysis and Renewable Integration, as well as the Industrial Automation and Instrumentation Control Masters. Both intakes are in October and February for the two I've mentioned. And we also are running a promotion for our professional certificates of competency. So what that basically is, it's our 3 month short courses which are run by our affiliated sister institution, Engineering Institute of Technology. So the professional certificate of competency, sorry, usually run around £133. But if you apply before November, we do have a discount, and I'll be putting that in the chat now. So that's for the professional certificate of competency. And then lastly, I just want to turn your attention to the what we call QR code or the link for the certificate of attendance for today's webinar. For those of you that just joined us, please note that you only have 2 days to fill out the form that I'm going to present the QR code for and the link. So once you filled that in, it will ensure that within 2 business days, you get the copy of the slides as well as the video recording of this presentation, as well as the certificate of attendance, but that will be sent to you within 4 business days. So just make sure all your information is correct so you do receive it. If it's not in your inbox, please check your junk and spam mail. And now you can just either capture the QR code or you can copy the link that I've put in the chat, and that will take you to the form that needs to be filled out for this um, presentation. And if there are no questions or anything else, we can call it a day. And once again, thank you all for attending. And
Kumar,
thank
can
you.
you give me 1 minute? There is one or two comments, and I just wanted to add to that.
Oh,
Do you
okay,
mind
sure.
if I just add to?
No, go ahead, go ahead.
D'Souza talks about, D'Souza agrees with me that human factors are always important. Believe me, D'Souza, you're absolutely top notch, absolutely right. So there's no doubt about it. Human factors are not only important, it's the most important. And D'Souza has gone a bit further than that, and he has given something which Engineering Institute has got a guidance on human factors and task-based risk assessment. And I think it's a great book, that one. And it's only published last year. So it's a very good publication. It talks about the different risk. And you can also see in Seagray's publications, a lot of things talked about. They've done a lot of surveys on human involvement. So I believe that that is it. And I hope that you have enjoyed today's presentation. I've enjoyed talking to all of you today, and I wish you all the best. So thank you very much, and thanks for attending. And I look forward to seeing all of you next month. I want to see all of you next month and bring all your friends. It doesn't cost you anything,
I
right?
can just
Is that right,
quickly.
Kumo, or did I make a mistake?
No, that's absolutely correct. I
I
just
don't want
want.
to be fired by ECT. I don't want to be fired by
Don't
ECT.
worry, you're all good. I just want to quickly give them the link for the upcoming webinars. So if they are interested in attending, they can always just use this link and see all our upcoming events for ECT. So let me just quickly put that in the chat for the attendees, and I'm sure they'll find this useful. There we go. So I have put it in the chat. Thank you all, and thank you to Dr. Kalam, and have a good day,
Okay,
good
bye bye.
evening, or
All
good
the
morning.
best.
Bye.
Bye. Good night. Sorry, it's good night here in Australia. It
Good
is,
night.
it is, it's, yeah, bye bye. We are always ahead of you, Kumo. We are always ahead of you. Bye bye.
Cheers, cheers.